All right, picking back up where we left off. What happens when I don't want to have this plus c as part of my answer? Well, if you're given a piece of information, if you're given some initial condition, you can actually use that fact, you can use that piece of information to end up solving for the c value, and then you can get something that's called the particular solution instead of the general solution. Okay, the general solution, that's the one where we're saying, hey, I don't really know what that constant is. I don't know the vertical shift on this function. I know all the variable parts, so I know the important stuff, but I don't know the plus c. I don't know that arbitrary constant that could have been on my original function, but then disappeared when I took the derivative. Right? General solution represents kind of all the possibilities that the graph could be with the given derivative. But if you have a particular solution, if you have some piece of information, you can actually use that to solve for the c value. And then once you have that updated function, it's called the particular solution. So let's go through and let's find it. Here we go. We got the derivative is equal to 6x squared. And then it says given f of 1 equals negative 3. We're going to use that to find the c value. Okay, now technically what we're doing, right, the derivative, f prime, that's dy dx 6x squared. Technically, what you're doing every time you integrate is you take this dx and you multiply it over, and you have 6x squared dx, and then technically I'm integrating the left. I'm integrating 1 with respect to y, which gets you to y, and then I'm integrating the right with respect to x. Now you don't really ever have to do that, but technically that's what we're doing, right? You multiply the differential over, and then you're integrating the left with respect to y, and the integration of 1 with respect to y is 1y, and then you're integrating the right with respect to x. So I add 1 to the exponent, 2 plus 1 is 3, divide by the new number, 6 divided by 3 would be 2. Okay, so there is your general solution. The one that has the plus c, that's the general solution. But if you have some piece of information, by the way, you don't have to do this. You can jump straight from the derivative to this original function. That's perfectly okay. And if you don't want to say y, you could go back. Remember, y is the same thing as f of x. You don't have to do this. That's just technically what's going on kind of behind the scenes. Whenever you integrate, you're kicking one of the differentials over. You don't integrate while you have a ratio of differentials. Right? Kick one over, integrate the left with y's, integrate the right with x's. But you don't really need to do that. If you're given the derivative, just integrate, get you up to the original function. Okay, so what if I want to use this piece of information to solve for the c value and settle not just for the general solution, but I actually want the particular solution? Well, let's look. Here it says f of 1 equals 3. That means the graph goes through the point 1, negative 3. Sometimes it'll tell you the information like this. Sometimes it may give you a coordinate point. But what that means is for this original function, if I plug in 1, I need to get out 3. Right? If I plug in 1, if that's my x value, my y value, what I get out is going to be negative 3. So we're going to use this. Right? So f of 1 equals negative 3. Therefore, the little 3 dots means therefore. For the y value, I'm going to plug in negative 3. And then for the x value, I'm going to plug in 1. Right? Plug in the x value, plug in the y value, and I can use that condition to solve for the c value. So you got negative 3 equals 1 cubed is 1. So negative 3 equals 2 plus c. That means your c value is going to have to be negative 5. Now, that's not an answer, right? You don't just put a box around c equals negative 5 and then call it a day. No, no, no. You take this c value and you come plug it in, and you get your original function, but you get the updated version of your original function. You got 2x cubed, and then instead of plus c, now I can take this c value and I can plug it in. And then this is the particular solution. Right, so the general solution, that's the one that's plus c. That represents all of the possible functions that have this as the derivative. Remember, the constant would go away when you take the derivative. But in particular, if I wanted to have this derivative and I want it to go through this point, so I want it to satisfy this condition, then I need to use that condition to solve for the c, and I can get the particular. Right, this is the only function that has this as the derivative, and that also has f of 1 equals negative 3, aka that goes through this point. All the other functions that have this as the derivative, their vertical shifts are different, so they would go through a different point. But this is the one that satisfies this derivative, and that goes through this point. Okay, so if you're given a piece of information, you should use it to solve for the c-value, because the particular solution is better than the general solution. If I don't have the information, the best I can do is general. But if I do have that little fact, if I have some piece of information about the original function, then I can use that to solve for the c-value, and if you have it, then you should use it to solve for the c-value. Okay, let's do this page, and then we'll be done for today. Solve the differential equation. All right, I need to scroll it down. Sorry. Solve the differential equation. Oh, and here it says y double prime equals cosine of x. Anytime you see this word that says solve the differential equation, I think the previous example was the same. Yeah, right, it says solve the differential equation. That just means tell me, what does f of x equal? Right? What is the original function? If it gives you the derivative, integrate once. Here, for this, it's going to give us the second derivative. But anytime it says solve the differential equation, that means what does the original function equal to? And if it starts you with the second derivative, you're going to have to integrate twice. Okay, so let's go for it. Here I got the second derivative. We're going to integrate once to get to f prime. And I know, hey, what would give you a cosine as the derivative? Well, sine. Therefore, the integration of cosine is sine. Remember, check. Is the derivative of sine cosine? Yes. And I would have plus c. So if that was my second derivative, here is my first derivative. Now let's look at the information that this question gave us. Do I have anything about this f prime level? Right? Thinking about kind of these different layers of functions. Going down the ladder is taking a derivative. Coming back up the ladder is integrating. Okay, so we started with the second derivative. We're going to have to integrate twice to get up to the original function. And when I integrate, right, anytime I go up from one layer to the next, that's when you put the plus c. Right? And if I have a piece of information, right, I integrated once, now I'm at this f prime level. If I have a piece of information at the f prime level, I want to use it to solve for the c-value. And luckily I do, right? It says f prime of 0 is 3, so I can use this piece of information right now to solve for the c-value. So f prime of 0 equals 3. Therefore, for the y value, or for the derivative value, plug in 3. And then for the x, plug in 0. Okay, so let's see. 3 is going to equal, now 0 is this point on your unit circle. The sign, the y-coordinate of that point is 0. So here the c-value is going to be 3. So let's plug it in. Now I know in particular, oh my gosh. Now I know in particular the first derivative. It's not just sine of x plus any random number. Now I know in particular it's going to be sine of x plus 3. So I use that condition to solve for the constant. Now we're going to integrate again. I'm going to integrate to get from the f prime level up to the original function. Okay, so let's integrate one more time. The integration of a sine is negative cosine. Careful, the really tempting mistake is to put a positive cosine. Just check. Is the derivative of a positive cosine positive sine? No, right? In order for the derivative to be positive sine, the original must be a negative cosine. So the better you know those trig derivatives, the easier the integration is going to be. But the negatives are a little tricky. Be careful. The integration of 3 is 3x. And then when I'm integrating this second time, I have that second constant, right? I could have had some mystery number, like maybe this was a plus 10, and then when I take the derivative, 10 goes away, right? When I integrate again, I'm going to have that second constant of integration. Even if you've already solved for the c and plugged it in, it's just not proper to use the c again. Use a different one, right? So you could use C1 and C2 if you want, or just like literally got like a bunch of other letters in the alphabet. Just use a different one. Integrate once, you have the plus c. When you integrate the second time, you have that second constant of integration. Okay. Now notice, the constants that you tack on, it doesn't have to do with the number of terms, right? Here you only had the one terms you integrated, you had the 1c, and then here, like, you don't need a plus d for the cosine, you don't need a plus e for the 3x. It doesn't matter how many terms are in your function, it matters how many times you integrate the function. And every time I'd go up one step in this ladder, every time I undo a derivative, you only need the one constant at the end. Doesn't matter how many terms are in that thing, it just matters how many times you integrate that thing. And every time you integrate, a new constant should come up. Okay, so now I'm up to the f level. Great. I have a piece of information about it, so let's use it. F of 0 equals -2. So I know the y value, set it equal to -2. Cosine of 0 plus 3 times 0 plus d. 3 times 0 is 0. That's lovely. Cosine of 0 is 1. Careful. So I got -1 plus d, which means the d value is -1. That's not the answer. Go back, plug it in. So this original function, in particular, is going to have to be negative cosine of x plus 3x, and then plug in your d value -1. When it says solve the differential equation, that means tell me what the original function is. And if it starts you with the second derivative, you had better integrate twice, which means you're going to have two constants of integration, which means I'm going to need two pieces of information. And this first example was kind of pretty nice because the information was spread out. I integrated once, but I had a piece of information about the f prime level, so I could plug it in right away, solve for the c. Then I could integrate again, get up to the f level, but I had a piece of information, right? That information was spread out. One of them at f prime, the other one at f. It may not necessarily always be that way. And let's see how to tackle those questions when it's not. Okay, next example. Solve the differential equation. Remember, that just means integrate, get up to f equals. Solve the differential equation. It says the second derivative is 2x squared plus, 12x squared minus 6. It says given f of 2 equals 3 and f of 1 equals -10. So in that previous question, right, I had one piece with the f prime level and I had another piece about the f level. But here for this second example, both of the pieces of information are up at the f level. So you're going to have to integrate all the way up to the f level and then somehow use both of those conditions once you're at that level. But if you don't have anything at f prime, you can't solve for the c value right away. Okay, so these questions are a little bit annoying. It's just going to end up being extra algebra at the end. But let's go for it. If it gives me this as the second derivative, let's integrate once and figure out what the first derivative, right? Add 1 to the exponent. So it's going to be x cubed. 12 divided by 3 would be 4. Right? Always check, is the derivative of this 12x squared? Yes, that means you integrated correctly. Then if I integrate this, add 1 to the exponent, -6 divided by 2. Check, is the derivative of this -6x? Yes, and then we integrate, we had the plus c. So gave me the second derivative. Integrating once gets you to the f prime level, but neither of these pieces of information is about f prime. So I got to keep going, right? I somehow have to get up to the f function before I can start using the pieces of information about the f function. So let's integrate again. We're just going to have to carry this constant up to the f level and then try to solve for it later on. Okay, integrate, add 1 to the exponent, divide by the new number, so it's going to be x to the 4th. Add 1 to the exponent, divide by the new number, so minus x cubed. The integration of c, right? If I was integrating, the integration of 5 with respect to x would be 5x. The integration of -17 dx would be -17x. Anytime you're integrating a constant, if you were integrating k with respect to x, it would be kx. Right? Anytime you're integrating a constant, all you got to do is tack on the variable. So the integration of c is going to be cx. And then since I integrated again, we have the second constant, so plus d. Okay, so now I've done the calculus. I've integrated twice. I got up to the f level. And now I'm going to use the two pieces of information. It's going to end up creating a systems of equations that we can solve to get the c value. and the d value. Let's use the first one. F of 2 equals 3. Therefore, if I plug in 2, 2 to the 4th power is 16, minus 2 to the 3rd power is 8, plus c times 2, so 2c plus d. If I plug in 2, it needs to give me out 3. And it says if I plug in 1, I'm going to get out negative 10. So f of 1 equals negative 10. So let's see. 1 to the 4th power is 1. 1 to the 3rd power is also 1. C times 1 is just c. And then plus d. And if I plug in 1, it needs to give me out. It needs to be equal to negative 10. So now I've got this systems of equations. I've got 2 equations, 2 unknowns, and I can solve it either with substitution or with elimination. Okay, let's try to simplify it. Here I'm going to have 2c plus d. Let's see, that's 8. Then I'm going to move that 8 over. So I had 3. Remember, this is all 8 over here. So I'm going to subtract the 8 to move it over. 3 minus 8 would be negative 5. And then over here I have c plus d. Then the 1s are going to cancel. How lovely. Okay, so I've got 2c plus d equals negative 5. C plus d equals negative 10. You probably would want to, if you add them together right now, nothing's going to eliminate. So what I could do is I could multiply this by a negative 1. Right, so let's do some witchcraft. Negative c, negative d, and then we'll just make that a positive 10. We're just multiplying it all by a negative 1 scale factor. Now I can add them together. 2c plus negative c. D plus negative d would eliminate. And then I had a negative 5 plus 10. Ooh, so look at that. C value is 5. Come back in, and you could plug it in. C plus d equals negative 10, or you could do this, the 2c plus d equals the negative 5. Let's see, if I plug it in here, that'd be 10 plus d is equal to negative 5. So if that's 10, and the answer is negative 5, that means this has to be negative 15. Okay, so if you have to, if that information's all top-loaded, if it's all up at the original function, you have to integrate up to that level, and then you're going to end up having a systems of equations, which, if you don't like elimination, that's fine. Use substitution, whatever. It doesn't matter. But you have to somehow use both of those pieces of information once you get to that level, which means, yes, you're going to have extra algebra, but no, that extra algebra shouldn't be the reason why you missed the question. Okay, then your answer, remember, take the c value, take the d value, and plug them in. So plus 5x, and then the d value was minus 15. So solve the differential means tell me what is the original function. If you have the information, use it to solve for the constants. We like it when the information is spread out, but if the information is top-loaded, you can still make it work. If I had to integrate, like if it started me with the 10th derivative, then you would need to integrate 10 times, which means you would have 10 constants, which means you would need 10 pieces of information, right? And we would really love to have one piece at the f level, one piece at f prime, one piece at f double prime, one at the 3rd derivative, one at the 4th, right? We'd like to know one piece of information for the original function and the first 9 derivatives. If the information was all spread out and I knew one fact about each level, it would be a long question, but it would be an easy question. Each one would be integrate, use the piece of information at that level to solve for the constant right when it appears, and then repeat, right? Integrate again. Use the next piece of information to solve for the next constant, and then repeat. If your information is spread out, you can solve for the constants right when they appear. But if the information is top-loaded, you have to kind of integrate up to that level, carrying the constants as you go. And then as soon as you get to the level where you have information, that's when you can plug in and you can start to solve for what those pieces are. Okay, so if you had 10 pieces of information, as long as they were spread out correctly, like hopefully one for each of the original function and the 9 derivatives, it'd be really easy. It'd be long, but it'd be easy. If you just had 10 points, right? By the way, this could have just easily told you 2, 3, and then 1, negative 10. If it would have given you the coordinate points, it's the same thing. If you had the 10th derivative and it gave you 10 points on the original function, you would be able to solve it. You would just have to integrate up to that original function, and then you'd have a 10 by 10 systems of equations, right? So you'd have 10 equations, 10 unknowns, and you wouldn't be able to solve that one by hand, very likely, unless it come out to be like very easy. More likely, you would need a computer or a calculator system to do that for you. We don't really ever get anything worse than a 2 by 2. But conceptually, if you had 10 pieces of information and you had to integrate 10 times, you should be able to do it. It would just be algebra work, but you should be able to do it. If the information is spread out and you know one piece at each level, it's a long question, but it's easy. If the information's all top-loaded, you have to just kind of carry your constants up to that level, and then you can solve for it. Okay, we're nearly done. Last one. Particle moves along the x-axis so that its velocity is given by v of t function. At time equals 2, its position is 3. Okay, so here we go. The position at 2 is 3, right? Translate this into the more useful notation, right? It gets kind of confusing with the x equals and the t equals. So the position at 2 is 3. So let's find the acceleration. Remember, we did kinematics when we did the derivative stuff. We have the original function. Take the derivative, that's your velocity. Take the derivative again, that's your acceleration. So to go from the velocity to the acceleration, you're going to take a derivative. All right, so the acceleration is the same thing as v prime. That derivative, that exponent's going to multiply to the front. And then the 5 would go away, right? So, and then you'd have the same domain restriction. So we know how to get from the velocity to the acceleration. You just take a derivative. But now it says find the position function. So if it wants me to go from the velocity to the position, I would need to integrate. So here we go. S of t would be the integration of your velocity with respect to time. So here we're going to integrate 4t cubed minus 3t squared plus 5. We're going to integrate it with respect to t. Okay, the integration of this would be t to the 4th power. The integration of this would be t to the 3rd power. The integration of 5 with respect to t, it's not 5x. It's going to be plus 5t. And then, of course, I would have that constant that would come up. And then I could use the piece of information to solve for the constant. So if I plug in 2, it needs to give you out 3. So S of 2 equals 3. Therefore, 2 to the 4th power is 16. 2 to the 3rd power is 8. 5 times 2 is 10. Plus C has to give you out 3. So see, that's 8. 8 plus 10, so that's 18. 18 plus what equals 3? Well, the c value has to be negative 15. It's really the same answer. It's the same function as the one on the previous example. I just got lazy and converted it to a kinematics question. I don't want to rework, get a whole new function, right? So there's a reason that it was the same as the d value was on the previous example. Okay, and then I have this c value. Let's go plug it in. T to the 4th minus t cubed plus 5t, and then plug in your c value minus 15. And then don't forget your domain restriction. There you go, right? So we can relate it back to kinematics. Just know, to get from the velocity to the acceleration, we just take a derivative. To get from the velocity to the position, we would integrate with respect to time.